Hello, and welcome back to another exciting installment of I Lecture Over the Slides. Got to find a way to keep it fun, right? This will be posted pretty much after it's ready, and then I will figure out um, what I'm going to do in lieu of what we would have done on Thursday, which would have been to um, do this worksheet on counterbalancing, but that's something that we'd have to do interactively together. And it's really nothing you're going to use this semester because you're not potentially going to be doing counterbalancing because we're not running experiments. So as I'm switching things up, what I might do is in lieu of an assignment or in lieu of a lab type thing, what I might do is start a discussion and have everybody sort of contribute to the discussion board on sort of ethics or maybe animal rights or something like that in research that we could have a discussion about. So stay tuned for that. But in the meantime, here I am presenting chapter 8. This week you should be finishing up second quiz, and I still have to adjust, I think, the time for a couple people, but we are going ahead and go on. Once we finish chapter 8, which is really, that'll be it. And then next week, we are done with chapters 6, 7, and 8. There is an assignment for chapter 8, which I will also put up after this lecture is finished. So you'll have till the end of the week to do that. And the next week, we will have our exam for chapters 6, 7, and 8. So, like I said, stay tuned. In this chapter, our learning objectives are looking at, since we spent a lot of time on frequency claims, we're going to do one chapter before we get into the meat of the class in true experiments. We're going to spend one chapter, which is this chapter, looking at scatter plots and correlations and association claims. Sorry, sounds like I got an email. We are going to estimate results from a correlational study and talk about how when we had a frequency claim, it was measured by, or it was factored by one measured variable. In an association claim, or what we know of as a correlation, that what qualifies it as an association claim or a correlation is that we have two quantitative, two measured variables. That's how we talked about that. That's a little review from chapter 3. We can look at the results using a scatter plot like we've been doing in the past few weeks, and we can also, of course, look at the results using an R value, or the regression value. So number 2, I will explain how the correlation coefficient, R, represents strength and direction of a relationship. We've looked at it in terms of reliability and validity. And now we can, of course, look at it in the main way we were used to looking at it, which is as part of a correlation. We will also analyze a correlational study in which at least one variable is categorical. So we do have two measured variables. Normally they're continuous variables, but we can still look at a correlation where one of the variables is categorical, one or the other, right? It's sort of a forced choice from, if we were to use terminology from chapter 6. In that case, we would not see a scatter plot. What we would see is a bar graph. Now, I don't want people to get confused, and I will be repeating myself a lot as I do in class for this chapter, because we generally associate a bar graph, 2 bars, with an experimental procedure, like comparing N versus I in the Stroop task. But in this case, a bar graph could also be used for a correlation only if one of the variables is categorical. Now, we can't have 2 categorical variables, but we can have one categorical variable and one measured number variable. And we can do that by using a bar graph. If it's 2 measured variables, then we would use the scatter plot as usual. You'll see what I mean. 4, we're going to interrogate construct validity of an association claim. So looking at the variables measured and defined the way that we want them to be. So we're asking, is the measure of each variable reliable and valid? So we're taking that idea of reliability and validity from chapter 5 and applying it to an association claim. We are going to interrogate statistical validity of an association claim. So we must ask about features of the data that may distort the meaning of the correlation, such as outliers in the scatter plot, effect size, and the possibility of restricting the range for lower than expected correlations. Why would we ever restrict the range? Well, there may be a reason, and I will go over that with you. In a scatter plot, one of the things that I should probably point out, if it's not super obvious, is that we always try to draw a line of best fit, which is that diagonal line or straight line or whatever line fits. But it is a straight line, which basically means that it is a linear equation or a linear relationship between the data, points of the data. But and sometimes when we get a correlation around 0, it might not actually mean that there isn't a relationship. It just may mean that the relationship is not linear. It might be what we call curvilinear. So in addition to effect size, restricted range, when the correlation coefficient is 0, we need to inspect to see if maybe it's not a 0 correlation, but that the relationship is curvilinear and not actually linear. If you don't know what that means, I will be happy to demonstrate as we go through this. I will also interrogate the external validity of an association by asking the question for an association claim of whom the association can generalize, and is it even important? We know that internal validity is not a thing for frequency claims. We know that internal validity has no bearing here. So what about external validity? Does external validity have a high percentage here? And I would really say it depends on what the correlation is asking, because if it is something that we can generalize to everybody, the correlation between, I don't know, GPA and success, well, anybody that's a student, we might have that correlation, so that could hopefully be externally valid to a lot of people. If you're asking about crazy cat person and measuring the number of cats someone owns and their level of sanity, well, then maybe that doesn't need to generalize to anybody. So really, I guess it kind of depends on, as we'll talk about, who or what the things are that you're measuring, and are we looking to see if this generalizes to a population of interest. And finally, we will distinguish an association claim, which requires that the study meets only one of the 3 rules for causation that we talked about in chapter 3, which is the covariance rule, from what we will be basically concentrating on the rest of the time, which is a causal claim. And that requires the study establishes 2 other things: temporal precedence, which means if you're saying that A causes B, then A has to come before B, and internal validity itself, which says that A and only A causes B. So anything that is due, any change that is due to C, D, E, F, G, or any of the letters of the alphabet, and so on, is not good. That's where we would control for those things, right? So 2 portions to the chapter: introducing bivariate correlations and being able to interrogate these association claims using the 3 of the 4 validities and showing why the 4th validity is null and void. So bivariate correlations. Bivariate means 2 variations or 2 things that you're comparing. So can you make correlations with more than 2 things? Yes. A lot of the times, though, what we end up doing is making individual correlations between 2 things. So you can have 5, 6, 7 things that we want to see if there's correlations, but we end up matching each one. So 1 versus 2, 1 versus 3, 2 versus 3, and so on and so on and so on. So to keep it simple, like I like to do, we'll just talk about 2 measured variables because that's the minimum requirement. That's the simplest way to look at this stuff, and so let's go with that. So what we see here is that there are 2 different ways to assess correlations or association claims. So we will be describing association claims between 2 quantitative variables, which is what we see on the left, and associations with 1 quantitative and 1 categorical data. So Um, Allow me to elaborate. On the left, we have two measured variables. We are looking at how well somebody is on a well-being scale, standardized to a Z-score. So basically, we're looking to see their level of happiness, and we are correlating their level of happiness with how many deep conversations they have. For me, as a total extrovert, I do not like this quarantine because I can't leave my house very much, but also because I crave human attention. I love having conversations, whether it's about psychology or about anything. They're telling us, by the way, I'm going to put this in an announcement, that they want us to keep trying to do virtual club meetings. So my Psi Beta club, I am thrilled at the opportunity to have and hold a Psi Beta meeting, even if it's virtually, because we can talk about cool stuff. Probably going to start with like the psychology of pandemics and some of the things that I talked to you guys about right before we left the last class, and ask the question of what sort of things do we see? The weird hoarding behavior, people buying guns and stuff like that. We see a lot of things in the news right now about people who are religious that are bathed in Jesus's blood, as I saw on one of the stations yesterday, on one of the news stations, because religious people are still going and risking it all to be in God's house of worship, I guess. I'm not criticizing the religious aspect. I'm criticizing the not following the rules that would keep us safe, or, try to flatten the curve. Anyways, back to this. So I crave deep talk, and what this is showing is that there is a positive correlation between well-being, how happy you are, and what percentage of your conversations are more than just like, hey, how's it going? How are we doing? How are the wife and kids? And more meaningful conversation. You can see it may not be a huge correlation, but you do see an upward trending slope of a line. So the happier people report to be, the more deep conversations percentage of their conversations are deeper than, a regular talk, a regular just, hey, let's catch up sometime. On the right, we also see two measured variables. However, one of them is a number. We're looking at marital satisfaction on probably a scale of 1 to 7. And the other variable, which is also measured, is a categorical variable. So it's asking, where did you meet your spouse? And there's only two options. You either met your spouse in an online format, a chat room or a dating app, or you met them offline. You met them somewhere in the real world. I don't really think there's an in-between. So what we're looking at is how satisfied people are with their marriage, whether they met online or offline. You may see that online is about 5.5 and maybe offline about a 5.3 or 5.4. So even though online is a little bit bigger, there's really no difference between them, according to the graph. I'm just looking at it. So if you have associations between two quantitative variables, on the left, we have a scatter plot. On the right, one of them is categorical, and it is a bar graph. Now, I know, again, you're probably trained in statistics, if you remember that far back, to think of a bar graph as experimental. And that's not necessarily the case. In this instance, I guess we'd say, in this instance, I don't want to sound redundant, although I will because I'll be repeating myself. We are looking at a bar graph, but it's two measured variables. In an experiment, as we talked about in chapter 3, a true experiment has to have one manipulated, IV, and one measured, DV, variable. So in this case, a bar graph does not mean an experiment because we have to look at the nature of the variable. In this case, we still have two measured variables. One of them just happens to be categorical. And so really, if you were to make a plot out of this one with the two categories, all you'll see is a straight line going up and down, as you'll see coming up. So again, I'm pointing this out, and I'm going to repeat myself until you're sick of hearing me say it. We call that, in Latin, that's ad nauseum, until it makes you sick. Associations, what makes a correlation or an association claim is that it is an association between two measured variables, which means if it is a scatter plot, that does not always mean we are looking at a association claim. Sometimes we're looking at it for reliability or validity. If it is a bar graph, that does not automatically mean, and you cannot automatically assume, if you're a good consumer and producer of research, you cannot automatically assume it's an experiment or a causal claim. Correlational studies, as this slide says, can include both quantitative and categorical variables, but they are just graphed differently. What makes a correlation, or what makes it an association claim, is the fact that there are two measured variables. That's right, repeat it with me. Some of you guys actually will. Two measured variables. All right, cool. Now we can move on, if my computer will let me. No? Are we being stubborn? There we go. Did I miss one? Nope, that's right. So again, as the guy is shouting at you, measured variables, not any particular statistic, not an F value, not an R value. Actually, it would be a T value. Make a study correlational. So just because I know that the conventional way of thinking about it was if you had an R value, it's a correlation. And no, it doesn't like me going back. So I'll just go back forward if it'll let me. Jeez. What makes a study correlational are two measured variables, because you'll get an R value for a regular scatter plot when you have two quantitative measured variables. But if one of them is a categorical and it's a bar graph, you're going to get a T value. So is it a T value that makes it experimental? No. Is it an R value that makes it correlational? No. What makes it correlational is that you have two measured variables. I said it again. All right. So looking here, a bivariate correlation means an association that involves exactly two variables. So in this case, they went from person A, B, C, D, E, all the way down to person double Z. And what they did was they measured two things. And this was that first graph on the left a couple slides ago. Your scale on a well-being, score on a well-being scale, anywhere from, in this case, 2.8 to 4.9. And the percentage of conversations that were rated as deep talk. And what you do is you just plot on the plot for each side, right? One variable along the x-axis, one variable along the y-axis, and you plot where it is. Person A had a 4.5 well-being, and 80% of person A's conversations were rated as deep talk. Person E had a 4.9, and 74% were rated as deep talk. What about somebody that had a lower one? Well, person double Z rated the score on their well-being scale of a 2.8, which is the lowest one on this list, and they have the lowest percentage of deep talk, 16%. So you can see that there's an association there. Person D had a 4.1 and had about 42%. Person B, a little off, 3.0, but had 52% of deep talk conversations. This, there are many other things in a correlation that may cause this. In this case, being outgoing and wanting to have deeper conversations may be one of those factors. So we're not looking to see causation. We're just looking to see that there is a trend or an association or a correlation between these two measured variables. And in this case, because they're both measured quantitative variables, we would put it in a scatter plot and look for a line of best fit. And the statistical analysis would give us an R value, or the correlational coefficient. Looking at the table, data from the table on the right, what we see here is, for table 8.2, is marital satisfaction. So where you met your spouse is categorical. You either can answer online or offline. So here we see person A met them online, and your marital satisfaction on a scale of 1 to 7, 1 being the worst, 7 being the best, is a 6.2. Person B met them offline, 5.5. Person C online, 7.0. Blah, 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 all the way down to person YY, which met their spouse online and has a perfect 7.0 rating. Oh, those are the days, huh? So what about table 8.3? What can we say about that? We see representative data from a study on multitasking frequency and ability. And you may remember this from a past chapter. We talked about looking at a correlation between the amount of multitasking or how often a person multitasks, and their accuracy score on a task for multitasking ability. What we should see is a negative correlation. And here, because both of them are numbers, we see the students, Alec, Jade, Sophia, Deangie, Max, all the way down to Yuri. And we see a quantitative score for the frequency of how many times they do it, and an accuracy score on a task. So we have two measured quantitative variables. Would that be in a bar graph or a scatter plot? Would it be a t-test or an R value? Yep, you are absolutely right, hopefully, if you guessed the way that I did. Two measured variables that are quantitative is going to be a scatter plot, and it's going to be an R value. But either way, whether it's 8.2 or table 8.3, both of them are going to be a correlation. They will just look different on a graph. 8.2, bar graph t value or t-test value, and 8.3, because they're both quantitative and they're both, neither of them are categorical, two measured variables, it's going to be a scatter plot and an R value. So looking back to that same first graph of percentage of deep talk and well-being scale, you can see that the line is increasing as you go from the left side to the right side, from negative well-being to positive well-being, which shows a positive correlation. What the correlation is, I don't know. We don't have an R value here, but there is a guideline, and you may have heard of Cohen's guidelines for evaluating the strength of an association. The R values are as follows. For an R that falls between around 0.10 or negative 0.10, it's a pretty small or weak association. Around 0.30 or negative 0.30, depending on the nature of the correlation. It is a medium or moderate one, and anything that is basically 0.5 or above is considered large or strong. The closer you get to 1 or negative 1, the more likely it is that there may be an actual causal relationship there. But again, we can't determine that from an association or a correlation. So if you're looking for strength of association, weak, moderate, or medium, and large or strong, 0.10, to 0.25 maybe to 0.30 is small or weak. 0.30 up to 0.50 is sort of a moderate or medium, and anything 0.5 or above is going to be a strong association. We think about this when we think about things like statistical validity, as we'll get into. So here we can see an association between that table 8.3, which was our multitasking ability, O-span score, and the frequency of multitasking. And here the numbers are kind of, or the points are kind of all over the place, but if you really follow the trends and you were to draw a line of best fit through this, you would find a downward sloping line going from the left to right. In this case, as you do more multitasking, or as your frequency of multitasking increases, your score on a multitasking ability decreases, because the more things that you do at a time, the less you can pay attention to each of those things. It's just science. So this would be considering a negative correlation, and you would have some sort of R value that starts with a negative number. Negative 0.3 maybe, I have no idea, because I don't know it. And I'm really not into drawing this line of best fit, but that's what it would look like, is a negative slope. So it would be a negative correlation. Not sure exactly how strong the association would be, probably a moderate one. Well, I guess we're missing the association here, but I can probably surmise from this slide that how do we graph when one variable is categorical? Guess what? We do a bar graph with a t-test and a t-value. When we analyze associations when one variable is categorical, again, we are looking at a t-test. So bar graph, t-test, where you're comparing the means of one to the means of the other. So if we were to use the example of online, offline, and the score on a marriage, satisfaction, we would have the mean, take the mean of the online scores, take the mean of the offline scores, and we would compare them. In that case, we saw like a 5.5 and a 5.3 maybe. We would, comparing them, your t-test would not give you a significant results because they were basically the same. So this is also a reminder, as if I haven't said it enough, I told you ad nauseum, right? I warned you that two measured variables are what make a study correlational, not the fact that you have a type of graph or a certain statistical value. It is the fact that you have two measured variables. That's what makes an association claim. That's what makes it categorical. And I know I'm repeating myself over and over again, but I do this in class and I make you guys repeat it too. So be thankful, I guess, that you're not having to do that so much unless I prompt you. So here again is what it would look like, as I promised I would show you coming up, if we were to put it as a scatter plot. You don't have anywhere to scatter because you have two categories. So all you're scattering, all you're doing is spreading out the numbers within that range. Online, you have ones that range from a little over 1 to a perfect 7. Offline, you have one that's below 1, and you go up to like a 6.7 or something like that. So in this case, you wouldn't have a line of best fit because each of these points fall in a line based on the category. So that's what it would look like if you were to try to make it a scatter plot, quote unquote. And yes, I did use air quotes when I did that. The best way to do this is represent it as a bar graph and get the means or arithmetic average of each of them. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 points for online. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, or 14 points for offline. So all we're doing is averaging those numbers together. You add up all their scores, divide by the number of people in each group, and that gives you the mean. 5.5 versus like 5.4 or 5.3. And what you can see is that there is no difference between the groups. People seem to be just as satisfied whether they met their spouse online or offline, according to this study. So the t-test, again, is a statistic that we use when we're only comparing two group means. So we would use a t-test, for example, in the Stroop task, when we're comparing people's scores on the N versus the I task. We would just simply add up everybody's score from their N task, divide by 10, because we had 10 participants in our class. We would take the I score, add up all the scores, divide by 10, and then we would use a t-test to detect the differences. Was there a statistically significant difference? So this is exactly what you'd be doing with one categorical and one quantitative measured variable. Online, add them up and divide to get your mean. Offline, add them up and divide, and the t-test is going to compare the two means. If you're comparing more than two means, that's when we'd use an f-test, but we'll get to that later. So again, we're asking what makes a study correlational? Well, again, the answer is having two measured variables. Doesn't matter if one's categorical. It doesn't matter if it's a scatter plot or a bar graph. Doesn't matter if it's an R value or a t-test. Yes, I'm repeating myself. This is the redundant chapter. What makes a study correlational or makes it an association claim is two measured variables. This is where we would do a, I would do a demonstration on the board. Looking at these things, we can see that I'll go through the example with you and I can tell you what it would look like because I don't really want to do the math. A researcher invited a sample of college students to a lab at 1:00 p.m. to take a control test called the Stroop. Oh, lucky for us, we've already done this in class, in which color names are presented in different colors. After finishing the Stroop test, each student wrote down what foods he or she had consumed in the previous hour, and the researcher figured out how many calories each student had eaten. Make a scatter plot of the table below. What kind of association would it be, positive, negative, or zero? Does the association seem strong or weak? And are there any what we call outliers? Well, what we see here is person A through I has how many seconds it took them to complete and how many calories they ate at lunch. So we can see that for person A, 100 seconds to complete, 550 calories. Person B took 120 seconds to complete, 200 calories. C would be 150 and 210, 80 and 600, blah, 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 blah. If I were to do this, I would simply put their scores in a scatter plot from 60 to 150, it looks like, and the calories from, I'm looking at 200 to 750. What it looks like in this case is a correlation that would be negative, because the more calories they consumed, seemingly the less time it took for them to complete the task. And I think the idea behind that is that the more calories you eat, the more hopefully energy you have, and the more you can concentrate, so the less time you'll take going through the test. Does that make sense? Again, we're not assuming causation. We're just saying that there's a relationship between, that it seems that the people who consume more calories were able to get faster times on the test. So in this case, it would be a negative correlation. Don't worry about if the association is strong or weak. If you really want to calculate this, you can stop right now and do a graph for yourself. In another study, the same researcher gave students a group test at noon. This time, maybe the next day, this time he asked whether students just had eaten lunch or not. So this is a yes or no, which makes it categorical, obviously. This time we would make a bar graph of the data in the table below. How would you describe the association? So here we see, again, person A through person I, and we see whether or not they'd eaten lunch. So in this case, I can actually pull out my calculator on my phone, so I will. And we can see, I'm going to calculate the yeses. So 80 plus 90 plus 100 plus 80 again plus 60 equals 410. And we have 1, 2, 3, 4, 5 yeses. So 410 divided by 5. It's going to give us about an average of 82 seconds to complete for the people that ate lunch. So keep that in mind. You can write that down if you want. 82 seconds for the yeses. For the people who did not eat lunch, we have 120 plus 110 plus 120 plus 130. That gives us 480. And there's only 1, 2, 3, 4 no's. So if I divide that by 4, I already know it's 120. So if we were to look at this as a bar graph, and we could do a t-test on this, which seems like it would be significant, we have, for the people that ate lunch and had calories consumed, that they finished the Stroop task in an average of 82 seconds. Those that did not have lunch and their concentration may have been impaired because they may be hangry or unable to concentrate because they didn't eat lunch, it took them almost 40 seconds longer on average to finish that test. I would venture to guess, I would stake my career on it, that t-test would be significant. That 82 seconds and 120 seconds is a huge difference, right? Trust me on that. So now we're going to look at interrogating association claims. I really don't like that this Chromebook has messed up or failed to convert my slides in the right way. Anyway, let's finish this off. So looking at interrogating association claims, remember for the 3 claims, frequency claims, association claims, aka correlations, and causal claims, we have 4 types of validity. Construct validity, I promise that these words of validity were a lot bigger in the original slides. But construct validity says how well was each variable measured. Statistic, which of course applies to all 3 claims, including this one. Statistical validity, which obviously we have a statistical value, either an R value or a T value. So statistical validity is obviously going to be of myriad importance for an association claim. How well do the data support the conclusion? Internal validity asks, can we make a causal inference from an association? Obviously, you should know right away. The answer is no, because, oh, did you repeat it? Did you say it before I even prompted you because we did it in class so much? Correlation does not imply causation. So internal validity, you are null and void from this conversation. And finally, external validity, to whom can the association be generalized? And really, the answer is it depends. It depends on what the association is, and does it need to be generalizable? A lot of the times the answer is no. Sometimes the answer is yes. So external validity, maybe, right? It depends. Construct and statistical validity, definitely. Internal validity, get out of here. So looking at construct validity, just a reminder, we ask how well was each variable measured? We have two measured variables, whether they're both quantitative or whether one is categorical. We still want to know that it was defined, measured. We have reliability and validity for each one. So the next question, was it measured reliably and with validity? Again, we go back to one of these tables, and we're looking at construct validity of association claims. This is the study on dating, online or offline, and marital satisfaction. So remember we talked about how we need to operationalize a variable. So we ask, how was the construct measured? So in this case, pretty easy, self-report. Did you meet your spouse online or offline? Or in this case, did you meet your spouse online, yes or no? Seems to be the only real way to ask that question. So I don't think there's any problem with that. Marital satisfaction was variable 2, and it was again a self-report. And your self-reporting answers to a 4-item couple satisfaction index, or CSI, not like crime scene investigators, sorry. Including, indicate the degree of happiness, all things considered, of your marriage, so overall, and in general, how satisfied are you with your marriage? Again, the responses range from 1, extremely unhappy, to 7, basically perfect on this test. We are relying on self-report, but I don't think this is anything that we can observe without it taking considerable more time and effort. And again, it's just a correlation. We're not trying to imply causation here. So seems to be pretty good. When we're looking at reliability, just a reminder, we have test-retest, internal, and inter-rater reliability. So do people give consistent answers to the question every time they take the survey? Hopefully the answer would be yes, but I guess it depends on the point in your marriage. For marital satisfaction, do people give consistent answers to the CSI every time they take it? If you're taking it, in the same time frame, probably. Internal reliability is not relevant because it was a 1-item measure for where you met. Internal reliability would be relevant for a 4-question satisfaction index or survey. They're asking, are the 4 questions that they ask you, the 4 items on the survey, correlated with each other? Does it have good internal reliability? And it should be yes. In this case, that means, would there be a strong Cronbach's alpha? Remember, Cronbach's alpha is your measure of internal reliability. And inter-rater reliability wouldn't be relevant for this because it's a self-report. Remember that inter-rater reliability is usually observable behavior, whether it's being coded through a videotape or people just watching through a 2-way mirror or, on the other side of the park, something like that. So inter-rater wouldn't have any bearing in it's null and void in a self-report survey. What about validity? We talked about the types of validity. So we can see, whoops, going back, I accidentally hit the button. Face validity and content validity. Well, does it look like a good measure of where people met their spouse? Yeah, because you only have 2 options. Does the CSI look like a good way to ask about marital satisfaction? Overall satisfaction, the degree of happiness you have, seems pretty good, I think. Face validity, content. Does it have all of the things that you want to know about in satisfaction, right? That would be content validity. Criterion. Do people's answer to this item correlate with where they really met their spouse? And man, it should. If you say online but you met them offline, then you're just lying. So it should have good criterion validity as long as you're telling the truth. Can your answers be corroborated with things like online membership records at dating sites or chat rooms or things like that? For the second variable, do people's answers to the CSI correlate with behaviors or outcomes related to satisfaction, such as things like divorce rate or number of arguments, or maybe, how much time they spent close to one another, intimacy or things like that. Convergent validity, is there more than one measure to where people met? Do they correlate with each other? If you met not in person, then whether you met in a chat room, whether you met on a social network, whether you met on a dating site, those should all correlate really highly. In the real world, it doesn't matter where you met or how you met. If you were introduced on a blind date or something like that, that should also correlate really highly, because at the end of the day, it's either online or offline. For the CSI, from variable 2, do the CSI items correlate strongly with a second measure of marital satisfaction that could be used in a study? There are probably other types of ways of looking at marital satisfaction, maybe a measure of chemistry. In fact, it was correlated 0.78, pretty good correlation. Remember, above 0.5 is considered a strong correlation. And discriminant, in this question about meeting on and offline, really getting at where people met, or something else as their ability to remember accurately? No, I think it's pretty good. We wouldn't really have anything discriminant, but if you met them online, it should not correlate with an offline thing, and vice versa. For the items of the CSI, do they correlate more weakly with dissimilar measures, such as personality traits like agreeableness or conscientiousness? If you guys ever took the Big Five personality test, those are dimensions of it. And sometimes opposites attract. So you wouldn't see a high correlation with a personality test between two people, between a couple, as well as the CSI. You would see that would be more discriminant. So we have interrogated our construct validity, and seems that those two are good ways of measuring it. They are reliable and they are valid. What about statistical validity? We talk about things like effect size, which is related to sample size. We ask the question if the correlation is statistically significant, even in an R value or a T value. T value right away gives you that alpha level of whatever it is. Remember, we're looking for 0.05 or below to be statistically significant. We can see that in a T value, and we can get that from an R value. So it doesn't matter which type of correlation, we're looking for the same thing. But now we're asking the questions, could this association be affected by things? The mean sometimes can be affected by really extreme scores like outliers. And this could also affect correlations too, especially if you have a lower number of people in the correlation. If you've got a correlation of over 1,000 people, one really weird extreme score is probably not going to do much. But if you only collected data on some of these examples, we saw like 12 or 13 people, one really weird high or low extreme score can really push the correlation into a number that is unreliable. We also want to ask, is there a restriction of range? And if we see a 0 or near 0 correlation, could it just be that there is no correlation, or could it be that the relationship is nonlinear, or in this case, what we call curvilinear? I will explain it if I'm allowed to move to the next slide. So forgive me for a second. It doesn't seem to be wanting to go. Do I need to? Oh, there we go. Make sure that yep, good. So when we talk about the strength of an association for statistical validity, one of the things that we should point out is a stronger correlation is also interpreted as a stronger effect size. Remember, effect sizes we talked about as weak or small, medium or moderate, and large or strong. So the higher the correlation, the closer to 0.5 or above, the stronger it is. 0.10 is weak or small, 0.30 is moderate or medium, 0.5 and above, 0.50 and above is strong or big. So a stronger correlation is going to give you a stronger effect size, as you see in two scatter plots looking at the different association strengths. The lines or the plots on the bottom graph B seem to be close to a line of best fit and seem to be going up in a stronger, bigger slope. So all things equal, stronger effect sizes permit more accurate predictions. They're typically more important, especially if it's just a correlation. So again, all things being equal, stronger effect sizes can lead to more accurate predictions and are more likely then to be statistically significant for an association or a correlation. When we look at strong correlations, again, we use this idea that stronger effect sizes can permit more accurate predictions. Looking at the difference in graphs A and B, what we see is Hugo's height at age 2 versus Hugo's own height at age 18. And this is a prediction chart or correlation chart that doctors use for pediatricians to try to figure out the growth charts and potential of where a child or how tall a child will be as they reach an adult age. And so predicting your own height at 2 and using a correlation to predict where you'll be at age 18 is a good correlation. Should have a more pretty accurate prediction. Nice strong correlation here, as you see. In this case, you're looking at, on the bottom, we're looking at the mother's height to try to predict the son's height. Why is this not as good a prediction model? Hugo's mom is, 163 centimeters. Hugo at age 18 is predicted to be 170 centimeters. Or he is 170 and his predicted height was about 174. Why is this not as accurate a prediction? Well, remember the way that genetics work is that it's not just based on mom's height, it's also based on dad's height and dad's family. So just trying to predict, it is much better and a much stronger, more accurate prediction with a bigger effect size, most likely, if you're trying to predict Hugo's height at 18 from his height between 0 and 2 than if you were to try to predict it from his mom's height alone, right? Again, the moral of the story here, stronger effect sizes permit more accurate predictions. If it's a combination of mom and dad's height, that might be close to or just as strong maybe as his own projected height from himself. So we know that larger effect sizes are usually more important. When we consider everything else equal, larger effect size is usually, almost always, considered more important than a small one. But there are some exceptions, so allow me to explain this. The biggest, probably, example of this, where small effect sizes, even though they are small, can still be important, is in matters of life or death. So what do I mean by that? Well, in this picture, which is supposed to be out of focus, the woman's face, because what is focused on is that she's holding an aspirin tablet. A lot of people take aspirin, of course, to reduce headaches and stuff like that, but aspirin is prescribed, over-the-counter aspirin is prescribed a lot for people who have high blood pressure. Because what aspirin does is it thins the blood out a little bit. Because if you have too much blood pressure going into your heart, there is a higher risk of heart attack. Or if you have too much blood pressure going into your brain, higher risk of strokes. So if you thin the blood out, what it does is help to try to protect against the possibility of a stroke or a heart attack. In this case, taking aspirin may not do much for some people, but it may help to save the lives of a few. So if you have 1,000 people and everybody takes aspirin, even though the effect size is really small, let's say that it prevents 20 of those 1,000 people from dying. It's still a really small effect size, 20 out of 1,000, but what that still means in life or death is that you've prevented 20 deaths. And we think of things these days with the virus and thinking about ways that we can be helpful, right? Because only a small percentage of people are actually dying, but it's life or death. So even if we, by doing this social distancing and the things that we're doing, wearing masks and doing the things that we're asked to do by the CDC, in life or death matters, even a small effect size is effective. If you save even a couple lives, you're doing a big service, right? So larger effect sizes are almost always going to be the most important. When are small effect sizes, when do they matter? Life or death, right? So we ask, is the correlation statistically significant? We're going to look at the logic of statistical inference. What does it mean to say that something is statistically significant? Hopefully you got a taste of that in Psych 1. Some of you that had me for it, maybe you don't remember back that far. And some of you, that are just fresh off of taking statistics, hopefully you understand what it means. And what does it mean if a result is non-significant? Also, what role does effect size and sample size play in significance? Well, looking here, one of the ways that we look at statistical significance is without having to see if the p-value is less than 0.05 on a printout or in a statistical program, is we can look at these little asterisks. So what we see here are the different correlations, and we have many different things that are being correlated, but they are usually put out in a table like this from a empirical journal article where we are looking at several different things, but remember, with bivariate correlations, what we're doing is looking at the connection between two at a time. So here we see when people are alone, when they're talking to other people, making small talk as a percentage of all conversations, substantive or deep talk conversations, and substantive percentage. So what we see here is intercoder reliability, looking at that. Small talk at 0.76, iffy, but the rest are pretty good, 0.97, 0.95, 0.84. Well-being index, so how happy they are, satisfaction with life, happiness, and their correlation on weekdays, correlation on weekends, correlation for personality differences. So you're going to get an individual one. So each score that you see is the correlation directly between those two things. So let's look at satisfaction with life and small talk as a percentage of all conversations. We see a negative correlation, excuse me, that's a negative 0.25, and we see one asterisk next to it. What that asterisk means, as you see down below, is that two-tailed, the p-value is less than 0.05 if it has one star or one asterisk next to it. So small talk and satisfaction with life. If you move over to the happiness one, we see 0.26 happiness and talking to others has a 0.26, kind of a moderate effect size. Correlation on weekdays, 0.27 between correlation with well-being on weekdays and substantive conversations, deep conversations. We also see substantive conversations as an overall percentage, 0.27 with weekends. And with correlation with personality differences. That means that it's significant at the 0.05 level. Then we see a bunch of them with two asterisks. Well-being index and being alone, negative 0.35. Satisfaction with life, negative 0.36, and being alone. Correlation on weekdays and weekends and being alone. A lot of this has to do with being alone, as you can see. But even substantive conversations and well-being, 0.31. And 0.28, we see two asterisks next to it. And if you look down below, right above where it says all else being equal, you see that that is significant at 0.01 or below. So that would kind of be really significant in that case, right? So we can see these different scores and how we can relate to them and know that there's statistical significance. If they have at least one asterisk, we know it's statistically significant at the 0.05 level. And if they have two, that it's statistically significant at the 0.01 level or below. What does statistical significance means? Blah, 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 blah. Statistical significance refers to the percentage of chance that the numbers we got were real and that we didn't get them by chance or by accident. So we have a less than 5% chance, if it's significant at the 0.05 level, of us reaching these numbers by mistake or by error. Or less than 1% chance. So that's a good thing. Again, all else being equal, stronger effect sizes, as you see, as you get closer to 0.3 or above, it becomes significant at the 0.01 level. So the stronger effect sizes are the ones that are more likely to be statistically significant. If you see the 0.08s and the 0.10s and the 0.03s and even the 0.20s of the world on this chart, this table, they are not significant. They don't have any asterisks. Anywhere from 0.25 or 0.26 in that range, 0.27 positive or negative, are significant at the 0.05 level. Anything above 0.28 or 0.29 in the 0.30s is going to give you significance at the 0.01 level. So again, all else being equal, stronger effect sizes, more likely to be statistically significant. When we have a case of outliers, much like affecting the mean, they can affect how the study is represented. If we're looking with more cases, like on the left, A and B, we see that there's one point that's really high and really far. Most of the others are below 8 on the y-axis, and between 0 and 4 on the x-axis. But there is one at the 4 that's way up there. It's a 4 on the x-axis and about a 14 or 15 on the y-axis. That is what we call an outlier. It's far away from the rest of the trend of the data, and that can actually affect the line of best fit. It can affect the R value. Here we see with a bunch of cases, and I'm not going to count them, but there's over 20 cases here. What we see is with the outlier in the data, the R value, the correlation is 0.37. So it's, moderate. Without it, if you took out the one weird, really extreme score, then the rest of the data is closer together, and we see a lower, less positive effect. What we see is an R of 0.26, which now is towards the weaker and not towards the moderate range. So just taking out that one score gave us a better idea of what the rest of the data looks like. Did it affect it that much? Well, about 10, 0.11, which is significant, but it didn't do a terrible amount of damage. Let's look at the one on the right. Here, we only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 points of data on the top and on the bottom. I'm sorry, on the top. On the bottom, we're going to have 11 because we're taking one out. Here you see again, 4 and 14, we see a really big outlier. With that in place, if we were to calculate it with that one, it's strongly influencing it. The less sample size you have, the more influence these individual points have. So that one that's way out here at 4 and 14, with the outlier still counted, your R value is at 0.49, which is pretty strong. When you take that one out and leave only 11 points of data left, your R value goes all the way down to 0.15, which is really weak. So that one data point skewed the numbers in a huge, huge way. What you want to do is try to be as representative of the numbers as possible. So if you do have these outliers, it is a good idea to remove them before you calculate scores. Outliers have impact when the sample size is bigger, but the impact is much greater when the sample size is small, as you can see. What about restriction of range? As you see here on top, the correlation is sort of cut off. We're looking at SAT scores, and we're looking at college grades or predicted GPA. Here, we're only seeing part of the data. As you can see, the scores go from 1,000 to 2,400. I think that was originally when I was back in high school, back in my day. No, we didn't walk both ways in the snow. I lived in LA and there was no snow, so don't worry, I'm not going to give you that. Anyways, the SATs went from 0 to like 1,600. And then at one point after I was in college, they changed it to go from 1,000 to 2,400. And now I think they're back. So when if you guys took SATs, it's probably back to that score. But these were what it looked like for a while. So in this case, we're restricting the range. As you can see on the bottom, there are the full set of scores from 1,000 to 2,400, and you can see that the trend is pretty similar. It's an upward slope, and as your SAT scores get better, we see higher GPAs for college. So why would we restrict the sample? Well, think about this. I know you guys are at a community college, but if you are wondering why you even take an SAT score to begin with, it's because with all other things being equal, honor roll, GPA in high school to get into a four-year college, extracurricular activities and things like that, there's still a lot of people getting about the same. So these standardized tests like the SATs are ones that are designed to give you an extra advantage to getting in. If your scores are higher scores on this standardized test tend to predict higher GPA success in the future. So schools that are, Ivy League or, your Stanfords or your UCs or things like that, that have a stricter standard for people to get in, you're going to restrict the range. Anybody under 1800 in this is not going to be considered for admission. We are only going to look at the trend of people scoring between 1800 and 2400. So that would be the reason to restrict range. There's not many other reasons in the real world that I can think of, other than you only want the people who score this or higher, right? You can think about that for sports as well. Only people that perform at this level or higher. So restriction of range does make a sample correlation appear smaller than it really is in the population, but in this case, it's because they're not going to consider people under that. So that's why they would restrict the range. So you have to ask yourself the question as you're evaluating these things for statistical validity: did they restrict the range or not? Am I looking at just a portion of the equation? Restriction of range, you're probably not going to deal with much more than college acceptance, right? So, but it is a good way to interrogate statistical validity in a correlation. So again, looking, is there a restriction of range? Here, it's going from 1800 to 2400. If you know that the test goes from 1000 to 2400, then you know that the range is being restricted and that it might not be as steep a slope if you were to take into account of all the data. Here, from 18 to 2400, you see a sharp incline of GPA. If you were to, again, go back and take everything into account, you can see it's not quite such a steady incline. So correlation between SAT scores and first-year college grades. So just to look again, I guess I could have just gone forward. If you're restricting the range, sorry, this is a repeat slide. It could be that your slope is affected by the fact that you're not looking at the full set of data and only a restricted range. Finally, we see something like this. If you saw something like this on a scatter plot, the line of best fit would basically be a flat line going across, which would mean zero or close to zero correlation. But look at the way that these lines, or these dots, I should say, sort of go together. In this case, we could connect the dots using a curve. It actually makes a U shape. If you were to draw a curved line going from 0 down to 20, 40, 60, and then up towards 80. What this is showing that the data in a scatter plot is normally looking for a linear line, a line of best fit. But in this case, with an R of 0.01, it's because the data does not fit a linear way, but it does have a relationship that is nonlinear or curvilinear. So in this case, what we're looking at is your age in years and how much you use the healthcare system. As a baby, you need to go for multiple checkups to get vaccinations, should your parents choose that sort of thing, and they should. So when you're a child and incapable of taking care of yourself, the amount of times you go to the doctor for checkups, monthly, yearly, all of that, is very high in your early years. As you become an adult, between the ages of 20 and maybe 50, a lot of people don't have, unless you have pre-existing conditions, the amount of time you use the healthcare system is yearly checkups, and maybe if you are broken bone or you're coming down with something and you want to go to the doctor to get medication for it. But the usage overall is pretty low. And then as you get above 60, and as you get closer to 80 or 100, as your DNA is breaking down, as people need to take more and more medications, as your body is unable to repair itself, you again have high usage and go to the doctor a lot. Prescriptions change, diagnoses can be impacted, and so we see just as high, if not higher, than when you were a baby or a kid. So in this case, there is a relationship. It's just curvilinear. It doesn't fit in a linear pattern. So that won't adequately, a line of best fit here would not adequately describe the relationship. This is curvilinear or U-shaped. If we looked at the effectiveness of a drug and a response, let's say that you're wanting to study for an exam. You're very tired. It's late at night. Your energy level and concentration level is pretty low. In the middle, you have maybe 1 cup of coffee or 1 energy drink or something like that. You're probably at a good spot. Right in the middle, nicely caffeinated, able to concentrate. But if you drank 6 cups of coffee or 6 Red Bulls, you're going to go right back down to very caffeinated, but very low concentration. So it would be the opposite of this. It would be what we call an inverted U, or as Dr. C would call it, an N, lowercase n. In that case, right, your optimal level's right in the middle, but the relationship is not linear. It's curvilinear. So the last thing we're going to look at is internal validity. That's all for statistical validity. In internal validity, we're looking to see if correlation can imply causation. Can we make a causal inference? Yes. I understand you already know the answer is no. Correlation does not imply causation. But we can use those 3 rules from chapter 3 just to see. So when is a potential third variable a problem? And can we make a causal inference? Well, let's see. Here are the 3 rules. We have covariance, number 1, temporal precedence, number 2, and 3 is internal validity. Again, one of these rules is still satisfied under a correlation. Number 1 is called the rule of covariance. Is there some sort of relationship between variable A and variable B? If there's no relationship, you don't even have a correlation. In this case, we don't have to specify the type of relationship, but there has to be some association, some relationship between A and B. And if there is, then we have a correlation. So if number 1 is met for covariance, this still is considered a correlation. What about number 2 in temporal precedence? That's directionality. Did A cause B, or did A lead to B, or did B lead to A? In a correlation, it does not matter which one came first in time. If we are measuring crazy cat person, it doesn't matter if we measure the number of cats first or if we measure the amount of craziness first. So we do not have temporal precedence, and it doesn't matter. If we cannot tell which came first, we cannot infer one causing the other, but we're not trying to. So we can see that already with number 2, we fail the internal validity test. And 3, the applying internal validity is the third variable problem. Is there something else that can cause both? Is there something else that can cause a person to go crazy and stockpile their amount of cats that they own? Probably, right? If there is a plausible third variable, in a correlation, it doesn't matter if something else causes it. I can use another example of low self-esteem and depression. Doesn't matter. Does low self-esteem cause depression? Does depression cause low self-esteem? It's possible that one could cause the other. They could cause each other. I'm not really sure, but yes, there's a relationship between them. So again, it would work for covariance, and we don't care. It would not meet temporal precedence because we don't know. Also, could something else cause both of those things? Could something else cause both depression and low self-esteem? Yeah, your boo, your bae saying, hey, it's not me, it's you. I don't want to see you anymore. Or, let's take this social distancing thing and just make it permanent. Yeah, that could cause both depression and low self-esteem, right? Sorry if that was a bad joke, but not sorry because I don't ever apologize for bad jokes. So in a correlation, it does not matter if something else causes the relationship between A and B. All we're trying to do is see if there is a relationship between A and B in the first place. So internal validity does not matter in an association claim. We only meet one of the rules for causal claims, which is number 1, covariance. And sometimes we can be looking at there could be a third variable that causes these things. Like I said, there could be a variable that's causing a change in both A and B. In this case, what we're looking at is on the left, our percentage of substantive conversations and our well-being score. And you can see that there are 2 concentric circles in there, blue dots and green dots. So there is a third variable in this case that would be an internal validity problem had we had it. We can see that majority of the green dots are well above and majority of the blue dots are well below. What is that third variable that causes maybe less happiness and less, definitely less substantive conversations? And it looks like it's education. So if you didn't guess, those in blue are that are lower overall are less educated, and the ones that are more educated, like you guys in college, right, seem to be happier and also seem to have deeper conversations. So there you go. In this case, on the left, looking at the circles, you would see that most of the blue is on the bottom, most of the green's on the top, and this would be an internal validity problem should we be looking at internal validity, right? Because that would mean that there was something else influencing the trend of this data. If you had higher education, that caused more substantive conversations and possibly more happiness. If you did not, you had less of all of the above. On the right, you can see that the sort of are mixed. And even though there's a little bit more blue on the bottom and a little bit more green on the top, there's a good mixture in the middle. So in this case, it would not be a problem of a third variable. So it wouldn't be an internal validity problem because there is a nice mixture if you were to average them out between less educated and more educated people. So, as it says on the bottom, sometimes a third variable would be considered an internal validity problem. Sometimes it's not. And if you look at the pattern of data, it can pretty much tell you the answer. Do we care about internal validity, though, for this chapter? Nope. I'm just pointing it out. So finally, external validity. Ask the question, to whom can this generalize to? To what other populations, people, from the sample to the population, right? We also have to ask the questions, as we talked about in the last chapter, how did they get their sample? Remember, a more representative sample overall is better. And does external validity really matter in an association claim? Remember, our short answer is, it depends. What about these things we call moderators? How do they address external validity? Well, here we can see, looking at this question, we're looking at multitasking, again, as the OSPAN test score, and we're looking at the time spent multitasking. Here we see that most of these, we have responses in O and Y. So these are two different types of people that are answering it. If you aren't sure what O and Y stand for, or if you think you know, I'll give you a second to try to guess, and then I'll tell you the answer. O stands for old, and Y stands for young. So it would make sense, the way that I talked about it at the beginning, that younger people who are more invested in multitasking and have been doing it for a lot longer tend to be better at it. Those who don't do it and don't spend as much time doing it tend to be the older generations of people. In this case, we would say that this may apply more to young people and not so much to old people for multitasking. Is this externally valid? For this one, probably yes. If you're a younger person, right? Your skills at multitasking may be a little bit better simply because you were always exposed to it and you've had more practice. What about a moderator? What is a moderator and how do we define that? Well, a moderator is one subgroup of people, old versus young, males versus females, things like that, where the difference is, if you were to separate them out, would be a huge difference between the groups. If the numbers are very close to the same, you would say that a variable is not moderating the relationship. If the numbers are far apart, like in this table, you would say that gender is a moderator variable. So, looking at the relationship between being extroverted and having group conversations, it seems that there was an association, a positive association, statistically significant R value, as you can see, between extroversion and the percentage of group conversations. But like the last graph, if we were to break it up into gender and say how much of the association is males adding to this between extroversion and group conversations and how much of it is females, well, we know stereotypically that females are said to have a higher vocabulary. They tend to socialize more. They want to talk, if we're, again, getting stereotypical, they want to talk about their day more, and guys just want to and grunt and go watch sports on TV when available. Sigh. So anyways, females in this group are statistically significant. Their association is 0.49, right below 0.5. So that's a pretty strong effect size. For males, you're getting hardly anything, 0.07, 7%, very weak, right? If that, less than 0.10. So because there's a huge difference, it seems that females are much more responsible for this association, and males contribute almost nothing. So if the scores are very far apart like this, what we say is gender is moderating the relationship between extroversion and group conversations. Here, looking at where moderating is not, sorry, gender, or this third variable is not moderating the relationship, looking, same idea, but what we see is the association between extroversion and being alone. Females are statistically significant at 0.05, negative 0.42. Males also statistically significant at negative 0.33 between extroversion and being alone. So it looks like they're both the same at 0.05. The scores are not that different from each other. 0.33, 0.42 are both in the moderate effect size range. So we would say that these are not, the gender is not moderating because the scores are about the same for each subgroup. For table 8.8, it asks, does weekend, weekday status moderate the relationship between deep talk and well-being? Whether it's, if it's a weekday, it looks like the percentage is 0.28, which is statistically significant at 0.05. On the weekend, it's 0.27, which is statistically significant at 0.05. And the difference between 0.28 and 0.27 is basically nothing. So if the numbers are really close together like this, it seems like both groups are scoring about the same. So you would say that it is not a moderating variable. If I go back and the scores are far apart, 0.49 and 0.07, you would say that gender is moderating because females are a majority of that relationship and males are not really much at all. So the sort of cheat sheet way of thinking about it, if the numbers like this are very close together, you would say that those groups are not moderating, and these are day of the week or gender is not a moderating variable. If the numbers are far apart like this, then you would say that gender is moderating that relationship because females have a high score and males have a really low score. So that's sort of the way to think about that. This might be the last slide as I go through, and I believe it is. I think this lecture has gone on long enough. I probably could have separated it into two, but I didn't really want to because I just wanted to get on through, break on through to the other side. And I know we usually take a break in our classes anyway. So feel free to break this up into however many lessons you want. But there is an assignment that we normally did in class sort of together. So I will type that up for you guys and present it so that you guys have time to do this based on this. There will be a portion on moderating variables. So if you wanted to go to slide 39 or 40 while you're doing it, it's probably recommended. I'll put that in the directions and I will talk to you guys next time.